Hi, chemistry. We're going to revisit covalent bonds again today, and we're going to talk about one last aspect of the covalent bond, and that is the covalent bond polar or not polar? So keep in mind we're talking about a covalent bond here, not an ionic bond. So we're talking about a bond where electrons are shared between two atoms. Now, you may have heard this term polar before. It's worth pausing here and thinking, where have I heard this term polar? What kind of things do I know of that are polar? And what do they do because they're polar? So we're going to talk about what that means to be polar and the effects that that has. Okay, so polar just means that the bonding electrons shift. The bonding electrons, which should be shared between two atoms, right? They should live in this area. They're actually going to shift towards one atom because that atom has higher electronegativity. So let's look at this in two examples. First of all, let's look at this in terms of hydrogen and hydrogen bonding. That would be the H2 molecule, right? So if we draw the H2 molecules with a Scott diagram, it should look something like this. The other one we're going to look at is hydrogen and fluorine. So that's the HF molecule, also known as hydrofluoric acid. Okay, so again, we're going to be looking at these bonding electrons. These bonding electrons exist between the two atoms. In HF, it's these two electrons. We're ignoring all the electrons that are lone pairs around fluorine and just looking at the bonding electrons. Now, remember, we're talking about an electron shift based on higher electronegativity. So if we look at this HH molecule here, hydrogen and hydrogen have equal electronegativities. That means that the nucleus of one hydrogen has the exact same pull on the electrons as the nucleus of the other electrons. So these electrons aren't actually going to shift towards one hydrogen. Why would they? There's nothing there that would cause them to shift. If we look back to force of attraction, the Z, or the nuclear charge, for both hydrogens is exactly the same. The distance of the electrons to the nucleus is also exactly the same. So these electrons do not shift. No shift in bonding electrons. Therefore, this is a non-polar bond. In contrast, let's look at HF. All right, so we're looking at the electronegativity of hydrogen versus the electronegativity of fluorine. This would be a good time to go back and look at the electronegativity periodic trends. What causes it? What are the trend left to right, top to bottom? And what you'll see is that hydrogen is less electronegative than fluorine, a lot less electronegative. And so these bonding electrons, although they are shared, they will spend some time around hydrogen. They will spend some time around fluorine. They're actually going to shift and spend more time around fluorine. And so what we get here is a fluorine that handles these bonding electrons for more time. Now, it doesn't take them. It's not an ionic bond. It just handles them for more time. And so fluorine actually gets a partial charge. So this is our symbol for partial. So fluorine's going to be partially negative. Hydrogen's going to be partially positive. So remember, electrons are going to shift towards the atom with higher electronegativity. And if shift occurs, if those bonding electrons shift because of a difference in electronegativity, what you get is a polar bond. Okay, I want to show you a couple of these. Here's exactly what we were talking about. So notice we have two hydrogen atoms. Here's hydrogen atom 1, hydrogen atom 2. You can see the electronegativity of these hydrogen atoms down at the bottom of the screen. And this dark gray cloud is actually where the electrons spend their time. So you can see that the electrons spend their time equally between the two hydrogens. The cloud is identical on both sides. Notice there's no partial charge. Partial charges are noted here. And this is going to be non-polar. This is something you should be able to predict. If I give you two atoms, you should be able to tell me, is the bond going to be polar or non-polar? Here are two fluorine molecules. So we have a fluorine-fluorine. You can see the electronegativity at the bottom. Again, because fluorine has the same electronegativity as the other fluorine, these electrons are going to be distributed equally. We get a very equal electron cloud here with 0 partial charges. Lastly, you can see the HF molecule. So notice we have hydrogen and fluorine. Here are the electronegativities for hydrogen and fluorine. You can see fluorine has a greater electronegativity than hydrogen does. And as a result, the electrons are going to shift. Notice that the cloud is bigger around fluorine, the cloud is smaller around hydrogen. So the electrons are going to shift towards fluorine. You can see there's a little gray arrow here. It's a little hard to see, but that shows you the bond dipole. A dipole is an arrow that shows you the shift in electrons. It shifts towards fluorine, that's why the dipole is pointing towards fluorine. It leaves fluorine partially negative. You can see it's a partial charge, not a complete charge. And then the hydrogen side is partially positive. That's why the dipole has a positive side, has a little plus sign on the positive side. So hydrogen is going to be partially positive because the negative electrons shift away. Fluorine is going to be partially negative because those negative electrons shift towards fluorine. So hydrogen, the bond between hydrogen and fluorine is going to be a polar bond. Okay, now you may be wondering, what does this affect? And that's a really good question. So before I show you what it affects, I want to show you one molecule, and that molecule is water. Now, we're not going to look at polarity across a molecule in our class, but because water is so common and water is such an important factor when it comes to polarity, we are going to take a minute and look at water before we look at what this polarity actually affects. Okay, so water, if you draw the Lewis dot diagram for water, it turns out like this. Okay, so again, we can look at one of these bonds. Let's look at this bond between hydrogen and oxygen. We know that oxygen is going to have a greater electronegativity than hydrogen based on our periodic trends. That's something you should be able to tell me. So therefore, these two bonding electrons in the middle are going to shift towards oxygen and away from hydrogen. So hydrogen becomes partially positive, oxygen becomes partially negative. Now, the interesting thing about oxygen versus these other molecules that we've talked about is, water versus the molecules on the other side is that there's two bonds for us to keep track of. And so the electrons on this side will shift towards oxygen, just like the electrons on the other side. But the reason molecules are harder to deal with than bonds is you have multiple bonds to figure out how do these bonds affect each other, and you have to know the molecule's shape. So we're not going to talk about the shape of molecules in our class this year. That's something we'll talk about in AP chemistry. But for the record, a water molecule is bent. Something like that. And so a water molecule is not in a line. So when we have bond dipoles, what happens is that they combine together and they form an overall dipole. If you've ever dealt with vectors in math or in physics, that's exactly what we're dealing with here. And so these two bond dipoles come together. If you can think of it like tug of war, right? If we have a rope here being pulled in this direction, we have a rope here being pulled in this direction, right? Is that center point of my rope going to move? Yeah, it is, because they're not being pulled in opposite directions, right? They're being pulled on an angle. If you have a box and you tie that box to two dogs, I don't know if I can, there's a dog. It's kind of like a cat. Or you tie your box to two cats. Either way, it could be a fun experiment for a whole nother set of reasons. Okay, anyway, you tie your box to two dogs, right? And the dogs pull at an angle. Is your box going to move? Yeah, your box is going to move, right? And that's exactly what happens with bond dipoles. These bond dipoles shift the electrons at an angle, and the electrons have an overall shift. So water is water has polar bonds, and it is a polar molecule. Now, like I said, you don't have to understand polarity in molecules. You just have to understand if a bond is polar or not. And then you have to trust me. Water is a polar molecule. I'm going to show you this with those similar diagrams. Okay, so here's hydrogen, oxygen. You can see a difference in electronegativity down here. You can see hydrogen ends up partially positive, oxygen ends up partially negative, and you can see there are two bond dipoles in this molecule. Now, when I click again, you're also going to see the molecular dipole. So same drawing, you can see electrons are shifted towards the oxygen, away from the hydrogen. And here, this little yellow line, box, that's your molecular dipole. So the two bond dipoles come together and form a molecular dipole, making water a polar molecule. Okay, you don't really have to understand anything on this slide as long as you know that water is a polar molecule. Okay, so covalent bonds do this. When you're looking at a covalent bond, you should be able to tell me, is that covalent bond nonpolar? And is that covalent bond polar? Is there no shift in electrons, or is there some shift in electrons? Now, there is a third category over here that we've already talked about. If you get such a big difference in electronegativity that the electrons get pulled away from one atom, that atom finally takes the electron, that's what we call ionic. So it's kind of a scale here between nonpolar, polar, and ionic, which is why sometimes we talk about ionic compounds like acids covalent compounds like acids having ionic character, right? They're so polarized that they have huge partial charges, and one of the atoms is very close to just taking the electron away from the other one. So this, we like to talk about distinctions, but really it's more like a sliding scale of the degree of ionic character. All right, so you should be able to tell me this. You should be able to tell me, is our covalent bond, is it polar or is it a non-polar covalent bond? Now, why do we care? Well, my dear students, that is an excellent question. Why do we care about polarity? We care about polarity because it affects everything. If you study chemistry, you will daily be interacting with polar or non-polar substances. If you go into health and you talk about medicine and what it does inside your body, is this medicine toxic? Does it build up inside your body? That's based on polarity. Will this skin cream interact with my skin? That's based on polarity. If you look at beauty products and you talk about waterproof versus non-waterproof mascara, that's based on polarity. It affects everything. When you talk about elements, atoms, compounds, and molecules, and then you start talking about what they do, you're going to talk about polarity. It's one of the first things you talk about. So it affects, we're going to talk about three big things. First of all, there's an effect in an electric field. It affects soluble, will it dissolve or not? And then it also affects attraction. So I want to show you a couple things that talk about why we care about polarity. All right, so this is hydrofluoric acid. Okay, this is an HF molecule, and you can see that they show you one end, the orange end is going to be electron rich, that's the fluorine. The blue end is electron deficient, that's the hydrogen. So they kind of show you the shift based on the size around the molecule, that's the electron cloud, and also colors. Okay, so in this, they had an electric field, and before the electric field, all right, before they turned the electric field on, the molecules were oriented any way they pleased. After they turned the electric field on, then the negative part of the molecule was attracted to the positive plate. So although it's just a partial charge, it still has an effect around other charges. And we can see a similar effect in the next molecule, which is going to be carbon dioxide.
They become oriented with your negative ends facing the positive plate and your positive ends facing the negative plate. So the CO2 molecule is non-polar.
Okay, did you hear that? The CO2 molecule is non-polar. The CO2 molecule has polar bonds, but the polar bonds cancel each other out. And the molecule as a whole is non-polar. So watch what happens when they turn the electric field on.
Notice that the orientation of the molecules is red. The field is off or on.
Doesn't affect it at all. So a non-polar molecule is not affected by an electric field. All right. Let's look at solubility. All right, I'm going to fast forward this, and you can see, okay. So they deal with salt here. This is table salt, so sodium chloride. I love how they take the salt cube and they turn it into your lattice with individual sodium and chloride ions. Now they're going to take water, remember, we just talked about how water is a polar molecule. Water is going to have a positive end and a negative end. So watch what happens when water interacts with salt. The partially positive end of the water is attracted to the negative end of the salt. So this attraction doesn't just happen in an electric field, it also happens with other molecules. The negative part of the water, the partially negative part of the water, is attracted to the positive sodium ion. And this is what causes things to dissolve. These charges attract other charges, and that's what dissolving is. The salts are pulled apart and suspended in the water, oriented around the partially positive or partially negative end of the water. And water has such a polarized bond that it dissolves almost anything. It's called the universal solvent, which is a really important property of water, and we talk more about that in chemistry. Okay, one last video to talk about attraction. So this is kind of a macroscopic view of the effects of polarity of water. I love this video. Let's watch this one.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and had to use equipment that was here on board the space station. We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's packed, it's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. So when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merit and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water is all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth. And then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations. Great idea.
Okay, so you can see Water, because it has a positive and negative end, not only is it attracted to ions in a salt, it's also attracted to itself. It's attracted to towels. It's attracted to his hand, right? It causes all kinds of attraction because of these partial charges. So polarity is really fascinating. It's really interesting. It affects a bunch of stuff, and it's caused because of a difference in electronegativity. All right, so let me know what questions you have on that. I will see you in class.